Right, I'm going to get started. So, hello, welcome to the H2STEEL workshop on steel, basically. So, we're going to be talking about energy, recycling, and innovation pathways. So, I wanted to talk to you a little bit about our H2STEEL project. So, basically, we explored and developed a sustainability assessment model for converting sludge into hydrogen and then an alternative carbon source for manufacturing steel products. And you can learn more about the project by referring to our website and also on our LinkedIn page as well. Just so you know, so we used a bunch of IE tools like life cycle assessment, prospective life cycle assessment, social life cycle assessment, and hybrid life cycle assessment to understand the proof of concept that we developed in a very lab scale. So you will find the results for this available on our website and also on our LinkedIn page again. And if you want to know more information about the H2STEEL project, you can reach out to me. Leiden University, we did the pretty much the work package 4, which we focused on analyzing the sustainability of this system. And you can also go again to our project pages and explore more. And there's a bunch of really amazing speakers today to talk to you about what steel and what they're working on. And I would like to give the space to them now. Thank you very much.
Excellent. Thank you very much. So the first speaker for today's workshop is Takuma Watari. He's going to be speaking about how circular and low emission is the steel we make and use globally. So I'll give the floor to him. And please, if you have any questions, just leave them in the chat, and we'll answer them after he finishes his presentation. Thank you very much.
Sounds good. I hope everybody can see my screen. Sounds good.
Yes, we can see.
Okay, sounds good. Yeah, thank you for the introduction. I'm Takuma Watari from the National Institute for Environmental Studies, which is I would say like the research division of the Ministry of the Environment, but I'm currently working at Leiden University in the Netherlands. Yeah, so I'm going to talk about this, how circular and low emission is the steel we make and use globally. Yeah. Okay. So yeah, I want to start my presentation with this rather complex diagram, which shows how materials and energy move through the global economy and turn into greenhouse gas emissions. And I think this system's view allows us to see which activities are actually driving emissions globally. So yeah, as expected, we see significant emissions from driving cars, running buildings, and making foods, which we actually often talk about in the context of climate change mitigation. But we can also see industrial activities to produce materials, including steel, produce even greater greenhouse gas emissions. So yeah, what we can say is the industrial sector is one of the biggest driver of greenhouse gas emissions, and the steel is the bigger driver. Is quite a major source of greenhouse gas emissions within the industry sector. So you know, in order to decarbonize the global economy, we cannot just focus on promoting electric vehicles, improving building ventilations, or installing more renewables, or maybe transitioning towards vegan or vegetarian foods, which these are all important strategies, but we also have to think about how we can decarbonize the industry sector within a limited time frame. So that's the main themes of my work that I've been doing over the last several years. Yeah, so in this context, making steel flows more circular is getting quite a bit of attention for decarbonization, basically. So yeah, World Economic Forum, OECD, and other industry organizations all highlight steel recycling and the circular economy as a key solution for deep and faster decarbonization. In this context, the World Steel Association says steel is the most recycled material in the world and is fundamental to the circular economy. But the key question is, how circular is the steel we make and use globally at the moment? And this sounds like a simple question, but the reality is we don't fully understand it because the data on recycled steel is not always available. And even when it is, the definition varies depending on the data set. So some of the data reports like collected scrap, not the recycled scrap. Some of the reports sort of show the part of the scrap, including forming and fabrication scrap, but not necessarily include end-of-life scrap. So there's lots of variation depending on the data set. So without having a consistent and standardized data, I think it's quite difficult to track progress or like compare different countries or like pinpoint the best way to improve. So that's exactly what we are trying to do in this work. Yeah, so what we did was basically collecting lots of data from industry reports, government statistics, and trade statistics, and reconcile the data inconsistency and structure the data as a multi-regional physical input table, as you can see on the right side of the slide. So so this is like a large matrix that that sort of record all the transaction globally. So we have a diagonal. So this is the domestic transactions on the diagonal. So this is quite an active transaction because this is the domestic transaction. But also we see international trade in the remaining areas of the matrix. So we can trace where the imported materials are coming from and where the exported materials are going to. And yeah, based on this reconciled data set, we've created the interactive Sankey diagrams to visualize how iron and the steel move through the global economy. So we can choose different countries we are interested in and immediately check the Sankey diagram for that specific countries. So this is the case of Malaysia's. And also we can track changes over time on the ER slider to basically check how the iron and steel has been evolving over time. So the data set covers world's top 30 steel producing countries over the last two decades, from the year 2000 until 2020. So these top 30 steel producing countries covers more than 95% of the total crude steel productions. So the basic idea here is to provide intuitive understanding of the scale of steel production, consumption, and recycling, rather than sort of overwhelming you with lots of numerical data tables, which are not always easy to interpret. So what we are trying to do here is to provide the data with a systems understanding rather than slowing a lot of data tables. Okay, so now we are looking at the snapshot of the current steel flows. So from the left, we start with iron ore extraction, which then move through the stages of iron making, steel making, forming, fabrication, and in-use stages, and the waste management and recycling down there. And what we can see is basically the global steel industry requires about 1,800 megaton of iron inputs for steel making, and about 600 megaton of that comes from recycling. So this means the global recycled content in the steel making stage is 33%. So steel is magnetic. It's quite easy to, relatively easy to separate from other waste streams. But despite this inherent recyclability and the decades of industry efforts, only about 1/3 of iron inputs currently comes from recycling. And I think important point here is this limited recycled content is not because of the poor waste management. In fact, what we can see on this right side of the Sankey diagram is that more than 80% of end-of-life scrap is currently collected and recycled. So the real challenge is the growing in-use steel stock, which is still embodied in like buildings, infrastructures, cars, appliances, and so on and so forth. So what we can see again on the right side of the Sankey diagram is that steel inflow into the use phase is about 3 times higher than the outflow, which means even with perfect recycling, without any process losses, recycling alone could only meet part of the demand. And this sort of imbalance between inflow and an outflow is not a short-term phenomena. So what we can see on this diagram is that over the past 2 decades, the global steel industry has made significant efforts to recycle more and more scrap, and end-of-life recycling rate has improved from about 60% to more than 80% from the over the past 2 decades. But at the same time, the EU steel stock has continued to expand, which means the scrap availability relative to demand has been declining during this time period. So the consequence of this stock expansion is the stagnation of recycled content in the steelmaking stage. So what we can see in this diagram is that over the past 2 decades, the recycled content of the liquid steel or in the steelmaking stages has been stagnated at about 30% over the past 2 decades. So in essence, the industry hasn't been able to close the loop because the the EU steel stock has been growing much faster than the improvement in the waste management stages, or I would say recycling efficiency. And of course, recycling status varies across countries. But when we analyze what kind of factors are actually explaining the regional differences in recycled content, then we found several important points listed here. So the first point is domestic scrap availability explains recycled content in some countries, such as the United States, China, and some of the Middle East countries, but it's not a determining factor in most cases, including the Netherlands and other countries. What we found was seemingly high recycled content in some places is often supported by low recycled content elsewhere through scrap imports or offshoring the production of high quality flat products. So what we found basically was regional differences in recycled content is not determined by how well these countries recycle within domestic borders, but rather determined by how these countries interact with international markets. So based on all these insights, we can categorize major steel producers into 4 main patterns, each basically reflecting the varying levels of recycled content for different reasons. So the first pattern is characterized by high recycled content, thanks to the abundant domestic scrap. So the key example includes the United States, where electric arc furnaces are predominantly used to recycle the abundant domestic scrap. And this EAF-based steel meets most of the steel needs domestically. So we have a thick flow from the scrap generation from the EU stock stage towards this electric arc furnace-based steelmaking. So this is a key feature in pattern 1. In contrast, pattern 2 is observed in more emerging economies such as China or India, where recycled content remains relatively limited because of the limited domestic scrap availability. So we see, relatively speaking, we have smaller scrap generation from the EU stock stage. As you can see here, and we see dominant ore-based steelmaking to feed the growing stock. So this is quite a contrast to pattern 1. And pattern 3 achieves relatively higher recycled content despite limited domestic scrap availability. So Thailand, for example, fits this model where rather than producing steel domestically, they sort of offshore the production of high quality flat products. So we have quite thick flow here, which is the import of flat products. So the central role of domestic steel industry in Thailand, for example, is recycle some of the forming and fabrication scrap rather than end-of-life scrap, or using iron ore to produce BF and BOF steelmaking. So this is a key feature in pattern 3. And lastly, pattern 4 shows the relatively lower recycled content despite having abundant domestic scrap. So Japan, for example, prioritizes ore-based steelmaking to produce and export flat products, as you can see here. So we have a thick flow here and here and here. So consequently, some of the scrap is actually exported to other countries rather than recycled within the domestic industry because of the difficulties in contamination control at the moment. So based on all these insights, now let's sort of step back and look how recycled content evolves as steel moves through the global economy or move through the global supply chain from liquid steel to finished steel products and end-use goods. So I think what's really interesting in this diagram is that recycled content varies widely at the steelmaking stages, as you can see here, but these differences start to even out as steel move towards the more downstream, such as in the fabrication processes or in use stock stage. So by the time steel reaches like car manufacturers, building constructors, or like end users like us, the recycled content looks much more balanced across countries, as you can see here. So we have a huge differences in the steel making stages, but not much difference in the fabrication or construction stages or actual use stage. So yeah, I think these kind of findings have quite important policy implications, because nowadays there is a growing push to set national targets for recycled content. But what our analysis actually indicates is that the recycled content is largely determined by global supply chain rather than the efforts within national borders. So if we do not consider this sort of global trade dynamics, setting recycled content targets on a country by country basis risks activating a resource nationalism movement and not necessarily improve the recycled content or global scale. So one of the conclusions from our study is that priority should be placed on stabilizing global stock growth. This means, especially in the high-income context, or the people in the global north, this means increasing recycled content should always come from using less steel, not using more recycled steel. So this is a bit controversial topic, but I think yeah, this is one of the conclusions from our work. So this is specifically for the global north countries. Okay, so now let's move on to the another question that I've been working on more recently, which is how low emission is the steel we make and use globally. And again, this sounds like a simple question. And in fact, we understand the greenhouse gas emissions at the production stage very well. So, how much of the greenhouse gas emissions are actually emitted per ton of steel we produce. But when it comes to consumption-based emissions, which is the carbon footprint of the actual use of steel-containing products like cars, buildings, infrastructures, or appliances, the picture becomes much more complex, because the steel is world's most heavily traded commodities, and the steel produced in one country often ends up in used somewhere else. So to answer this question properly, we need to track the steel flows across the global supply chain and link them with the greenhouse gas emissions. So what we did in this study, this is the ongoing work, but what we did was link the global facility level greenhouse gas emissions dataset with the which basically covers more than 1,000 iron making and steel making facilities globally. And I linked this dataset with the multi-regional physical input table that I explained earlier. So yeah, this sort of helps us to track which country's consumption is actually driving steel-related emissions globally. So here's how we define the system boundaries. So we include all the major processes in the iron making and steel making. So yeah, such as coking, blast furnaces, basic oxygen furnaces, electric arc furnaces, and subsequent casting and rolling processes. So the system boundaries include emissions from fuel combustion, chemical reactions, on-site electricity generation, but all other emissions from, for example, off-site electricity generation, off-site heat generation, or any emissions credits are excluded from the system boundaries. So yeah, this is basically how we define the system boundaries, and you can find more details in this report. So yeah, again, the work is still ongoing, but here's the first results we got. So on the left side of the slide, we see production-based emission intensity in the world's top 30 steel producing countries. And what we can see is some countries actually, so like Thailand, Italy, Spain, or United States, are operating relatively lower emission steel industries, and seems like they are leading the way towards global decarbonization. By the way, this dashed vertical line indicates the decarbonization benchmark for 2030, 2040, and 2050. So what we can see is 10 out of 30 countries already meet the 2030 benchmark from a production perspective, and Thailand even achieved 2040 decarbonization benchmark and close to 2050 benchmark. But when we look at the consumption-based emissions, the picture becomes completely different. So what we can say is low emission domestic production is often enabled by imports of steel produced elsewhere with emission intensive process. So we have a huge differences in the production-based emissions, but yeah, this difference is again as similar to the recycled content, even out as steel moves towards the downstream. So from a consumption-based perspective, no country meet the 2030 decarbonization benchmark, let alone the 2040 or 2050 targets, because the low emission domestic production is often offset by the emission intensive imports. So when we look at where this kind of emissions actually happen due to our use of steel containing products, then what we can say is, most of the consumption-based emissions actually take place outside the domestic borders. So this figure shows the origin of consumption-based emissions across the globe. And this black line indicates the domestic emissions, and the other colored line, the area indicates the emissions happening outside the domestic borders. So what we can say is in 22 out of the 30 countries analyzed, more than half of the consumption-based emissions actually take place outside the domestic borders, as you can see in this figure. For example, if you look at the Netherlands, most of the emissions actually happening not from the Dutch iron and steel industry, but quite a bit of emissions are happening in China and Germany and other couple of countries. So basically what we found in this study was the 7 largest steel producers, meaning China, India, Japan, US, Russia, South Korea, and Germany, collectively account for over half of most countries' total consumption-based emissions. So these countries hold the greatest leverage in determining the emissions profile of steel, regardless of where the steel is ultimately used, basically. So yeah, this means efforts to decarbonize the domestic iron and steel industry are not enough for most countries, because even if we can eliminate emissions from the domestic industry, imported emissions would continue to drive its carbon footprint if we maintain the current trade structures. So the decarbonization at the point of production does not always guarantee the decarbonization at the point of use. And now I'm kind of thinking about what do these results actually mean for industry policies and strategies such as CBAM, Climate Club, Scope 3 reporting. I'd like to hear your opinion, comments, or any questions on these results or topics or discussion points. With that, thank you very much for your attention.
Well, thank you very much. I think we are ahead of time right now.
Okay.
I don't think we have any questions so far. But anyways, if we have any other questions, please just write them in the chat, and we will make sure to read them before we finish the rest of the presentation. So yeah, I think now we can go to our next speaker, Ekinsu Akdogan. She's going to be speaking about integrating the life cycle assessment and techno-economic analysis to discover the potential of the emerging hydrogen plasma smelting reduction process in Europe. So I'll give the floor to her. Please, Ekinsu. You have your microphone off.
Okay. I
There
hope
you
now
go.
it's
Thank
on.
you.
Thank you so much for the nice introduction. I am a PhD student in KU Leuven, and today I will explain you a part of my PhD research topic, which is integration of life cycle assessment and techno-economic analysis to discover the potential of an emerging steel manufacturing technology in Europe. You should expect to listen more methodological oriented presentation, but to make it a little bit more interested, I will also show my preliminary results. So as previous presenter also explained very well, we all know that steel manufacturing is quite environmentally polluting process, and it is responsible of around 8% of global annual CO2 emissions. And to keep going our modern lifestyle, we expect global steel production to even increase more for the next decades. Therefore, we really need to find ways to lower these environmental emissions linked with the steel production. An H2 Plasma Red project proposes that hydrogen plasma smelting reduction could be the solution for this problem. because HPSR process can produce high quality steel without releasing greenhouse gas emission. At least that's what it has potential for doing. And how? Because using hydrogen plasma, iron oxide can be reduced to liquid iron, and instead of emitting CO2 or carbon monoxide or other gases, we see a release of water. However, HPSR is currently at technological readiness level of 5. TRL is a concept that expresses the development stage of an emerging technology, and TRL 5 indicates that the technology is validated, but in a partial scale, in a small scale. And H2 Plasma Red project aims to upscale this to TRL 7 by 2028, which is validating it in the commercial conditions. However, we know that steel manufacturing is a quite established industry. So in order to replace the current technologies, the alternative ones should be economically competitive, technically advantageous, and also environmentally must have low footprint. And that's exactly what my interest is. I am trying to understand by looking at the information we get from low-scale experiments, the potential and future of HPSR, and if it is better than the alternatives. And to understand this answer of this question, I will be using certain tools. LCA is one of them. LCA quantifies the potential environmental impact of a system across its life cycle, which can include raw material extraction, manufacturing, distribution, use, or end-of-life parts. LCA is standardized under ISO framework, and this frameworks define LCA principles, requirements, and guidelines. Techno-economic analysis, on the other hand, evaluates the technical performance and economic feasibility of a new and clean technology that aims to be environmentally better with respect to the technology currently being used. Unlike LCA, TA doesn't have standardized framework, but it mostly focuses on only material extraction and manufacturing parts. These tools can be integrated, and this will provide a more accurate decision-making support for policymakers and industrial stakeholders. By reading together the results of environmental impact, economic viability, and technical analysis, we will be evaluating the process systematically by minimizing inconsistencies and optimizing the indicators of these 3 different pillars. And they answer different research objectives. LCA mostly focuses on identifying environmental hotspots, projecting the future impacts under different scenarios. It searches for the results of benchmarking. It deals with uncertainty. TA, on the other hand, is mostly about cost hotspots, evaluates technical competitiveness. It also explores future prices across different scenarios with benchmarking and uncertainty analysis. And when we integrate these two, the perspective becomes more holistic, and the research objectives expands to understanding the trade-off between the costs and environmental impacts. It reveals potential synergies and conflicts, identify parameters that are sensitive in both dimensions, and ultimately supports a better, more informed decision-making process. So these were the basics of the tools I will be using, but I wanted to also show you how am I gonna use this tools. So the first step is to sketch the process flow diagram of low-scale production. The experimental data from TRL 5 and 7 experiments will be used to understand the mass energy balance and process flow diagram, which will eventually be used as a part of LCA in this scale. But things becomes more tricky when we want to understand the TRL 9 level of production. Here we need to upscale this process flow diagram obtained in low scale by using certain strategies. And this projected process flow diagram then will be used to do prospective LCA and techno-economic assessment. They will be merged with multi-criteria decision analysis, and this integrated assessment will be used to understand the potential of HPSR in Europe and policy recommendations that increase the potential of HPSR. I must say that all these steps are handled with continuous iteration, because currently the low-scale experiments are ongoing, and whenever we, for example, the partners optimizes the process more, we reiterate our upscaled model, and of course the rest of the parts as well. And in the first half, in the first half of my PhD, I mostly focused on the LCA part, which today I will talk most about this part, but also I will mention the rest of it. Before immediately start explaining the assessment details, I would like to talk about 3 important factors that are the building blocks of the LCA and TA assessments. These are system boundaries, critical performance factors, and benchmark. Since this part has significant impact on the results, it's really important to give well-thought decisions to determine these. So we decided to limit the system boundaries with raw material extraction and manufacturing steps. Here you see 2 different layers. One layer is the part that shows the part of the model that relies on direct measurement, which is HPSR part, and the rest of the system boundaries, which includes extraction, hydrogen, and electricity production. They are considered as background systems, so the information, the data we use for these parts will be from literature. Since LCA and TA results often used to compare the current technology with an alternative, we often need to understand the benchmark process very well as well. We decided to use natural gas-based direct reduced iron followed by electric arc furnace as the benchmark technology. We have several motivations to give this decision. First of all, this process has similar final product as HPSR, which is liquid crude steel. Second of all, we expect in the future that natural gas in this process have potential to be replaced with hydrogen. So in the future, for a better and improved comparison, we can update this model very easily. And lastly, since this is an already commercialized process, we thought we can access the data very easily from the literature. Critical performance factors are the important parameters that play significant role on the final process and assessment results. Since HPSR is an emerging technology, it is difficult to project its final optimized process flow. Therefore, we want to determine all the future possibilities and conduct a scenario analysis on these critical factors. I divided this into 2. First category indicates technical scenarios, which are more system level scenarios. This includes various HPSR configurations, varying process efficiency and iron ore quality. That can also include the recycled content as well. On the other hand, integrated scenarios explore the interactions between economies, climate, and energy. They integrate the socio-economical development, technology evolution, policy, etc. Therefore, they are very useful for the estimation of the future macroeconomic situations. Remind is only one of the integrated assessment scenarios. It's modeled by Potsdam Institute, and there are many other integrated scenarios as well, which will be used in this assessment to understand the future. All right. So now, moving to the LCA part slowly, I conducted as 3 different LCA models. The first one is the TRL5 experiment. This reactor has capacity to produce only a few kilograms of liquid crude steel per trial. The LCA model fully relies on experimental data, and we consider this type of LCA as attributional LCA. Attributional LCA is the type of LCA where we expect partners and inputs and discussions. And the LCA that is conducted for this one will be used to understand the potential hotspots. The second LCA model is for the pilot scale experiment. It has potential to produce a few hundred kilograms of liquid crude steel per trial. It doesn't only contain experimental experimental data, but a part of its process flow diagram is projected as well. And this is also an attributional LCA. We expect to use the outputs to understand potential hotspots and understand the parameters that contribute most to these hotspots. Lastly, commercial scale LCA is the capacity to produce tens of tons per hour of steel per hour. All the data is fully projected, relies on fully projected model. This type of LCA is considered as prospective, and naturally we expect to get more answers from this LCA, including potential future hotspots, benchmarking, global and local sensitivity analysis, and with scenario analysis as well. This LCA results, this is the summary of some of the LCA results, and it is purely for demonstration reasons. So we saw that increasing HPSR technology maturity, we saw lowering environmental impact due to optimized process conditions. And on the other hand, what we saw is that the high maturity HPSR has significantly lower environmental impact than benchmark, reaching almost 98%. Another result shows that the environmental contribution analysis of each scale of LCA shows a shift from material and natural gas inputs to electricity and hydrogen being the most influential on environmental impact. So there is a shift from materials to energy carrying inputs, which says something very important, which says that we should really read together the electricity and hydrogen manufacturing developments in the future to understand the potential of HPSR. This result shows that only the upscaled LCA, we checked 3 different scenarios and projected the year 2050. we assess 3 different scenarios. Baseline scenario is the extrapolation of today's trends, while optimistic scenario is basically the scenario where countries reach their climate goals, and ambitious scenario is the case where Paris Agreement conditions are satisfied more or less. What we see here is that baseline scenario has the most causes the most environmental impact, while other macroeconomic scenarios can significantly lower the environmental impact of HPSR. But to see why the electricity in the baseline scenario is more dominant, but hydrogen production is more dominant in optimistic scenario, we need to closely look into the processes used within the scenarios. The electricity mix scenario today, this is today's electricity mix, mostly relies on fossil fuels, and we expect the same trend for the baseline scenario as well. While optimistic scenario use less fossil fuels and more renewable energy, and ambitious scenario uses almost 100% renewable electricity. Very similar issue we see for the hydrogen production. At the moment, the hydrogen produced is all coming from steam methane reforming, which is quite environmentally friendly. While hydrogen mix baseline scenario is also very similar, but going towards optimistic and ambitious scenario, we use more and more renewable hydrogen, more green hydrogen. These were the results from LCA models. I will mention briefly my ongoing work about the rest of the methodological part. I'm planning to conduct TA only for industrial scale process and for benchmark. I am aiming to estimate CapEx, OpEx, and revenues of the emerging technology. I might use 2 different strategies. One can be calculating it manually or using a software such as Aspen Plus, and the information that will be used to estimate these factors will be collected from partners or public reports. This estimation will be followed by calculation of net present value, payback period, internal rate of return, and levelized cost of steel calculations. And we will be discussing these results together with the process efficiencies and cumulative energy demand. This is how I'm gonna integrate LCA and TA more or less. This is a very, very general framework, but with time I'm hoping to make it more significant. It starts with aligning the goal and scope of environmental and economic assessment. Then matching system boundaries and assumptions should be built. After calculating the indicators of the 2 assessments separately, then we merge the results together with hotspot sensitivity and scenario analysis. And also multi-criteria decision analysis is a very important tool to be used. I would like to say a couple of words about multi-criteria decision analysis as well. MCDA techniques evaluates multiple conflicting criteria in decision making. It helps to do rational choices, and it involves the perspectives of different stakeholders. As you can see, there are a plethora of MCDA techniques. I haven't yet choose which one to use, but I am hoping to even combine some of them and have an improved and most transparent decision analysis as possible. To conclude, with our initial results, we saw that the potential of HPSR should be read together with the developments in the electricity and hydrogen sector. So it is not an independent technology, but it's really depending on the developments in other sectors as well. Integrated LCA and TA bridges the environmental and economic perspectives in steel decarbonization by aligning the scope, system boundaries, and assumptions, and by multi-criteria decision-making techniques. And my next step is to merge TA with the ex-ante LCA model that was built. My last words will be about policy and how the results of this study can be used by policymakers. First of all, it will enable to weigh the trade-offs between three different pillars transparently. It will tell us under which conditions the technology can be competitive and the effect of carbon pricing on our net zero goals will be understood by the end of this study as well. Lastly, different scenarios for each possible future scenario will be understood as well. Thank you very much for your attention. If you have any questions now, you can ask, or you can contact with me anytime for more questions or more discussions. Thank you very much.
Thank you very much for a very complete presentation. I think we have a couple of questions here. I think we can answer them before leaving to the break. The first one is for Takuma. Okay. It says, can lower post-use scrap recycling affect the increase in consumption-based emissions? And would it be possible to elaborate in detail on some of the data sources used for obtaining prospective steel input flows and assumptions? I'll leave you to it.
Yeah, thank you for the question. So I think it's a bit complicated because I didn't dive into the time series data on consumption-based emissions. So the data, at least currently, cannot provide a direct answer to that question. But for the first part, for example, like if some countries increase the use of post-consumer scrap in their steelmaking facilities, while also increasing the dependencies on imports of finished steel products, then the consumption-based emission doesn't change basically, or it can actually increase. So it all depends on using the more scrap what does actually mean for the downstream trade flows. If it does also reduces the imports of finished steel products from other countries, then it can reduce the emissions, but it also depends on the condition of the steel demand sector, I think. And for the second part of the question, I'm not really sure. Does it mean for like using the prospective LCA probably?
Sorry, can I talk? Yeah. So in the diagram you showed, Takuma, there was a really nice chart on how it changes over time.
Mhm.
And I was wondering how you got those data, or how you initially modeled the electricity consumption separately for European countries, for an example, because it's usually available as one region, not separately.
Right. Oh, I see. Yeah, so there are actually a couple of initiatives that look into this sort of space. So like Energy Monitor and a couple of other organizations look into each facility and estimate emission intensity from each facility. So the data set that I use covers around 1,000 iron making and steel making facilities, but also other people also look into the similar data set. So I think that's quite a strong foundation for thinking about the future, because without understanding the current situation, it doesn't really make sense to look into the future. Right? So I think this kind of data set is now emerging. So I think this can be foundation for prospective analysis for sure. Yeah.
Right. Thank you.
Okay, thank you very much for that answer. Now, for the second question, it's for Ekinsu. It says, how exactly did you upscale the foreground processes? Did you use productivity coefficients or simulation softwares?
That's a very good question, and one of the most tricky parts while doing prospective LCA. I wasn't involved in that in the upscaling part, um, but I got the upscaled model from company called K1 Met, which work very closely with HPSR upscaling, and they used a mixed approach by using simulation software and also process engineering approach. So they mixed both of this by using experimental data they got from their facilities.
Okay, thank you very much. I hope that answers both of your questions. We have a little break. It's up until 12:06. Uh, we are ahead of time. So what do you think about getting back here at 12 o'clock? Would that be good?
By 12, I think that should be fine for, yeah.
Okay. Well, see you back in 12 minutes, okay? Thank you very much, everyone, for being here. And let's just take this break and we'll see each other in a bit. Thank you. Okay, welcome back, everybody. I think most of us just remain here. Well, for the third presentation of today's workshop, we have Petr Hradil. He is going to be speaking about modeling and quantification of environmental impacts of steel recycling and reuse. So, Petr, I give the floor to you, and just go ahead, please.
Okay, thank you very much. Yeah, my name is Petr Hradil. I work at VTT Technical Research Center of Finland, and I'm really happy to be here because these presentations that we've seen so far are really very interesting and I think very important. I was a little bit afraid if my presentation is not out of topic, but now I kind of feel that probably it fits here very well. But we will see. You can just give me some feedback afterwards. It is based on two European projects that we had recently. One is called Progress and one is called Advance. And you see that they are both like talking about reusing and circular economy. Basically, yeah, the decarbonization of steel sector can be, of course, done by decarbonizing steel making, but reusing is another possibility, actually, how to reduce carbon intensity of steel by producing steel without steel making. So these are like two approaches, and many times we see that there is kind of feeling about competition between those two approaches. So some steelmakers feel that this is kind of taking scrap out of them and taking their business. But these projects were both supported by steel industry. Progress was by Ruukki and Advance by ArcelorMittal. Modern steelmaking companies are really progressive, and even ArcelorMittal is now embracing new business models with actually reusing of components. If you look at the picture, you probably see now that I will be talking about constructional steel mostly. And if you look a little bit more closely, you will see that this is actually not a construction, this is a demolition. Purkupiha is a Finnish demolition company, and definitely the truss that is laying on the ground is not scrap. This is something that can be really used again. It looks very clean, but you can see some dirt there on it. But this is how maybe modern demolitions should look like, extracting very valuable products from buildings. So if we are talking about constructional steel, we are now having like overlap of two industries, steel industry and construction industry. Construction industry is almost 40% of global CO2 emissions. 11% is in materials. Steel industry has 8% of global emissions, but if we talk about CO2, it should be about 11% as well. And there is some overlap because we have a constructional steel. So this is about 5.7% of global emissions, if I count well. But you see still this is very big number globally, and it's worth actually investigating it and trying to reduce it. When we are talking about reusing, we don't have a very good data. I think in Takuma's model, it was not really considered so much because the data is just coming. Some models already exist. For example, Citra was modeling how much reusing of different materials would decrease emissions. And you see that about 20 megatons per year could be reduced by reusing of different building components, and steel is about half of it, so maybe about 10 megatons CO2 per year in Europe. So these kind of models and some statistical data are now starting to appear, but it is much more difficult to collect this kind of data because the industry around reusing of building components or about reusing of constructional steel in particular is not very much organized yet, and data is not systematically collected. Even on European level, we are only collecting data about scrap, about waste that is produced, not about waste that is prevented. So this is a little bit more difficult. But if we look at the emissions on the product level, we have environmental product declarations, of course, and ArcelorMittal's X-Carb steel, I think you would agree that it belongs among the best steels that we can get on the market. Maybe it is not the best, but the emissions are pretty much low, 333 kilograms of CO2 per ton in the product stage. At the same time, we have already environmental product declarations for reusable steel from European Metals Recycling, which is saying 47. So reusing from the user's perspective, it's already 86% reduction without implementing any expensive technology. Actually, it could be even cheaper than recycling in some cases. So if you are not really fan of reusing and you are taking the stance that recycling is the way to go forward, I am not really going to fight against you. But the thing is that reusing is happening. And when we are talking about quantifying of environmental emissions, we have to always take both sides into account. We have to count on recycling and reusing at the same time, because the material that is not reused will be recycled. The collection from of scrap from buildings is over 95% nowadays in Europe. So the material that is not reused will be recycled definitely. There is also many advantages actually why we are promoting reuse also of steel specifically, because we can really dismantle and rebuild the structures many times, even bridges and big halls that were designed to be only for one life, they can be at the end serving for multiple lives, and the lifespan is really could be very long if you are preventing the damage like by corrosion or some plastification. Also, very interesting thing is that steel has an indirect impact on other materials. You could see that steel is maybe not the biggest player on construction field. The biggest player is no doubt clearly like this concrete, but we can use steel actually to reduce emissions of concrete by creating such connections like you see here. And we can reuse the whole concrete blocks. And this indirect saving can be really great here. So also for timber construction, we can have dismountable joints and these kind of things. So there is a really very big potential and a very big role of steel in the future buildings, which will be designed not based on cost, but based on CO2 maybe. So that's something that should be also considered. Okay, and because we are talking about construction industry, you know, this is very much regulated environment. Because of the long lifespan of the products, the responsibility actually for the safety and everything is mostly on the national authorities, which are taking over this by issuing different permits and limits and requirements. So we have a lot of standards and we have them mandatory. So on the product level, there is a product category rules EN 15804. And for steel, there is also complementary product category rules for constructional steel EN 17662, which exists as a pre-standard at the moment. And the outcome is environmental product declaration, which is used also in other industries, but I suppose that it is not mandatory. In construction, it is going to be mandatory very soon because of the construction product regulation that is now requiring also environmental product assessment. So every CE marked product will have this calculation. If we go on the building level, we have EN 15978 standard how to calculate life cycle assessment of buildings. We have levels guidance for the more like comprehensive assessment. and the outcome is whole life carbon declaration. So now on the building level, the requirement is only to calculate carbon over the whole life of the building. And it is again compulsory since 2026. We will have limits and methodologies in all member states. So which is outlined in Energy Performance of Building Directive. It will be part of the energy certificate of the building, and national authorities will have to define methodologies, databases, and limits for it. So this is kind of environment where we are now kind of operating, and many things are really compulsory or becoming compulsory very soon. So there is really a strong need from the whole industry to move on and create very clear and very understandable rules and databases and methodologies. And because we are looking in the recycling and reuse of steel, we should first probably look in the EPDs, environmental product declarations. You have seen some of these EPDs already. So the material flows are reflected, of course, in the product stage where the material is produced. And then in the end of life stage, where the material is disposed or recycled. This is the main parts of the life cycle information. Partly also in use stage B, where the material is replaced and repaired and maintained. And also in the construction, you can have some extra material coming into and out of the process. So the left side of this is basically all the emissions and impacts that are created during the life cycle of that building. This is something that we are focusing now because we are trying to kind of save ourselves from the climate change effects. On the right side, we have supplementary information which are impacts beyond the system boundary. And these are impacts created indirectly by producing the particular product, which is then substituting some other product which doesn't have to be produced in the future, because this one can be recycled, or it can be reused, or it can be converted into energy or fuels. So these are impacts that are mostly happening after the end of life of this building. And because buildings have 50 years, usually design life, these are happening very far in the future. They are not really saving ourselves, but they are probably saving our children and grandchildren from this effect. So they are also important. And materials are reflected in the secondary materials part in D1, where recycling and reuse is happening. So in this presentation, I will be talking about both parts. Life cycle information on the left side is pretty much straightforward, so I will not spend so much time, but the supplementary information is still pretty much confusing for many people, and I think I could spend a little bit more time explaining what does it mean and how it should be properly calculated. So what should we expect from the left part, from that part that is happening now and which is creating this life cycle information for the current system that we are assessing? So we can have like new material, which is kind of, let's say, blast oxygen furnace, could be about 2,000 maybe kilograms of CO2 per ton. This is what Steel Association's number from 2011, so probably there is some updated number. You know that by recycling scrap, we can really go down to 300, 400 kilograms of CO2 per ton, or maybe even lower by decarbonizing energy. And by reusing, we can go even lower, like to 46, which is kind of insanely low compared to virgin material production. So this is like 3 levels what we could kind of expect on the production side. In the end of life side, these numbers are not yet very much collected and consistent, but we can see them in some EPDs already. Of course, disposal of steel is not happening so much, but it could be happening in then modules 1 and 2 is demolition and transport, C4 is disposal. So this could be quantified pretty much easily. In the case of recycling, we have also demolition and transport, C1 and C2. And then this waste recovery is C3. And according to standards, we calculate all the impacts that happen until end of waste process. So if you are not familiar with end of waste process, this is a legal procedure how to declassify waste that can be used again in production of new products. And for steel scrap, there is a European regulation, I think it's called, so for end of waste of steel scrap. So the rules are on European level. They can be also on national level or on some specific product level. Concerning reuse, the situation is not so clear because basically we want to say that reused product is not waste. But standard is saying that we should calculate impacts until waste is ending. So there is a little bit controversy in the standard. So we have still like question marks here, and this should be clarified maybe in the next editions of the standard. And we propose this kind of clarification in our project, saying that if we have a component that is not hazardous and we want to reuse it and we know who is the next owner, it is not really disposed and it fulfills technical conditions, for example, some harmonized standard, then it is reused and it maintains this product status. And in other cases, it is waste according to EU legislation. It is legally waste and it has to go through end of waste process somehow. It can be, of course, reused again, but it became waste before it, so it's a little bit more complicated. It can be recycled. This is what happens now. So there are some options here, and you can read more in this link about our legal recommendations. So far, there is a provisional a formulation in EN 15978 saying, okay, even in this reuse pathway, there is a waste happening, but only for the purpose of the standard. So we can have a boundary condition, we can have cutoff criteria for life cycle assessment. Otherwise, we wouldn't have any definition. So this is only for the purpose of life cycle calculations. So this was very briefly about the impact on the left side of the table. I think now on the right side is more interesting because we can have combinations of different scenarios. We have new material that is disposed, new material that is recycled or reused, or we can have recycled material and you can do the same things with it, or we can have reused material and you can do the same things with it. And if you look how module D1 looks like, it might be very confusing for you in the first sight. For example, the first line is really linear scenario, and you see that D1 is 0. And the last one is the most circular scenario that you can actually imagine, and D1 is again 0. So it doesn't make sense, maybe. But the thing is that the module D1 is not really a measure of circularity, of absolute circularity. It is measuring of the change of circularity relative to the current situation. So if you don't have any change, if you don't do worse or better, you have 0. But if you are doing better, you have negative values, which are good because negative values are decreasing your impacts. On the other hand, if you have a very good scenario in the beginning and you are not able to guarantee the same scenario at the end, you will have positive values which are not good. So if you imagine that you have your product that is already reused, but you for some reason cannot say that it is reusable again, you will have to declare positive numbers here. So this is what should we expect from module D1. It is consistent with product environmental footprint methodology, also circular formula, where it is aggregated together. So, but how we report it in the construction sector? So we report these things separately. So module A and C, which are compulsory, so you can see product stage and demolition stage. they can be put together and we can have some like carbon, for example, emissions. Module D is always reported separately, and you see if you have new material and recycling, module D is negative. If you have new material and reusing, module D is more negative because reusing is better than recycling, and you have more saving here. If you have reused material and you recycle at the end, you suddenly happen to have positive module D, and that's okay because your perfectly reusable construction for some reason is not reusable anymore. So that's a problem, and you have to acknowledge it in the life cycle assessment. If you have reused and reuse, your module D will be about 0. Okay, there is a little bit negative because we are not reusing the bolts or some small parts of the building, but otherwise it's about 0. So this is how you should understand this end of life formula and the tables that we have in environmental product declarations. How it is calculated is maybe a little bit more complicated. The methodology in EN 15804 is saying that we should make a difference between output and input. These are the orange flows, out and in. And we should make a difference between impacts connected to recycling on reuse. This is this EMR, and impacts related to virgin material production or average input material. While the average is only mentioned in normative, in informative annex, this is not normative, so it kind of creates a little bit unclear situation what should be there. And some people are saying if we use virgin material, we are greenwashing and we are overestimating. So this is one story that I want to debunk here. On the other hand, you can see that there is a sum, so we can explode this into different lines. And one can be used for recycling, and one can be used for reusing, and another one can be used for different recycling. So basically, this is what we want to do, because we want to use both recovery operations for the same product or for the same product system. So in Progress project, we have, by the chance, came in the same year with the same kind of equations as the standard. We didn't collaborate with the standardization group, but this was the outcome, and you see this is completely the same. It has only 2 extra yield factors that are coming from World Steel Association methodology for scrap recycling. So if you know that World Steel Association methodology, you know what is the yield factor here. It is efficiency of recycling process. This method is now in this pre-standards for steel. And we are now saying that VM must be primary production for recycling, but also for reusing. So this must be a theoretical steel that is made 100% from virgin materials, even if such steel doesn't exist, but this is because of closed loop recycling. So we anyway are substituting virgin material, even if we are not producing pure virgin material. And you can read explanation about this reasoning even in ISO 14044, which is saying how to allocate impacts for closed loop and open loop recycling. But maybe you noticed that World Steel Association released a methodology in 2024 that's dealing with reuse and recycling, and it presents much more complicated calculation. And also the flows here are much more complicated. You see that there are 2 extra flows which are happening, which are actually saying how much of steel scrap was coming into your product before it was reused for the first time, and how much steel scrap is going to be recovered from your product after it is reused for the last time. So in your current system, you might not have any scrap coming in or out. It can be completely reused and reusable product, but still you must know what is the initial scrap input and what would be the recovery if your product is not reused in the future. So this is much more complicated. It is a system expansion which is going beyond current system. and the equations are really difficult, but we could reorganize these equations a little bit, and we will see that they start looking very similar to the equations from European standards, EN standards. So there is a difference between some flows in both in recycling and in reuse. And there is a difference between some emissions, primary and recycling, or remanufacturing, and plus some extra things over here. And we have also some this efficiency factors Y and Z here in the World-Steel Association methodology. So by the chance, actually, yes, we can actually analyze it a little bit more here. These are the meaning of those extra things is extra credit for initial and final scrap. So basically, this is already what we had before, plus this is extra, and this is the credit for initial and final scrap. On the other hand, we have something less in reuse part, which is subtracted LCI of scrap in the product. And this means that basically XM must be virgin material production, because this is what you do if you want to have your real material impact. You will take virgin material and you will subtract scrap value out of it. So this is exactly how you would calculate it. So there is no like magic into this number, but it has to be a little bit reorganized here. So by the chance, we had in 2024, we had a project which is called Advance, and we could work on this methodology, and we translated World-Steel methodology into EN methodology, because European standards should be used for European environmental product declarations. So you see, basically, we renamed all the variables into the naming convention of the EN, and we changed some plus to minus signs because we need the benefits to be negative, but otherwise it is more or less the same. And you can read it in our report here, how to use it. So now the question is, we have now two methods. One is on the left side, which looks very simple, and it is also covered by Progress Project and by EN standards. One is more like complicated, and it's covered by World-Steel Association now, but it is also used in some EPDs. So companies are very fast, actually, like ArcelorMittal, for example, and some couple of other companies have already used this kind of like accounting for this initial and final scrap. So what is better? So we have tested it, and actually we found out that they are the same, even if they are using different parameters and they are like different flows. So the result for module D is the same. I would say almost. So this is almost the same. So the problem is that we have to dive a little bit into some calculated scenarios here. So we have calculated different scenarios with different reused input and outputs, and inputs and outputs, and 50% reused output. So basically we calculated with both methodologies, Progress and SEN methodology, and Advance and World-Steel Association methodology. And the result is really the same. Total is minus 1.44 here, or plus 1.06, or minus 2.49. So this looks pretty much promising. We can use even the simpler methodology, and we don't need to know extra parameters. But if you look in the table a little bit more carefully, you will see that the parts related to recycling and to reuse are different. So the emissions that are attributed to recycling and to reuse are different, because part of the emissions that should be attributed to reuse in the first methodology were moved into recycling in the second methodology. So this is making actually this difference here. So, well, I mean, as long as we are looking in the final number, we are okay. But if we want to see what is the effect of recycling and what is the effect of reuse, we are now in a trouble, because we need to choose the methodology. And if we choose the more complicated, which is maybe more realistic, let's say, we need to have parameters that we normally don't have. For example, imagine a company that is buying used products and selling them again for that as a reusable one. They don't know how much scrap is in the steel of the products. They have no way to find out this information themselves. So they should use some generic data or something for it. So, well, the methodologies exist. We have compared them. Is it too complicated? Yes, it is too complicated, but we think that we shouldn't force people to calculate it manually. This should be pre-calculated in APDs, and we have also some software tools that can calculate it. You can look in our web page and download the software to your mobile. There is also web version. If you use it only in APDs and some big companies are pre-calculating these things, I think it should be the best way forward. And as a summary of all these things, reusable steel does not become waste. Module D should not be aggregated with other LCA modules. It should not be added to them because it doesn't make sense. Module D shouldn't be reported even if it is positive. Some people are trying to hide it, so that's why we are highlighting it. As long as it is reported as a single score, it is okay. It provides the same result, but if it is required to separate it, then we need to clarify the methodology and maybe have some more research into it. Yeah, and we can use it also for some other materials. So this is the goal, actually, to have more like bulletproof methodology for other materials as well, that we can compare our products at the end. Yeah, so I think I used my time actually here. So I am happy for questions, and the QR code is directing you to our web page, where you can read all the information, also not about LCA, but also on the other aspects of reusing. Thank you very much.
Well, that was a very, very complete presentation. Thank you so much, Petr, for your presentation. I think we have a question for you. A couple of questions, actually. The first one says, are there any emissions or energy-intensive intermediary processes that are needed to purify, upgrade construction steel before reuse, or can they be used as they are? And also, can it be a substitute for the rising demand for steel scrap?
Yeah, okay. So the first part, it really depends. They're not. The reuse is a wide spectrum of operations. Sometimes you can use it as it is. That's true. For example, the picture that I had in the first slide, it was basically only cleaned, and the emissions were almost zero, like associated with it. There is only transport, cleaning, and re-erecting. Sometimes you need to cut and weld. So this is maybe some energy-intensive process, but compared to production of the whole steel, it's almost nothing. We are well fitting in that 46 kilograms of CO2 per ton. Sometimes you need to decoat it, and especially if you want to remove zinc coating, that could be a little bit intensive. But this is very rare when you want to remove zinc coating. Usually you will keep zinc coating. So these are only things that come to my mind. Substitute for the rising demand for steel scrap? No, I think it is actually it is actually diverting more steel from scrap. So I think actually there will be even more scrap missing in the market if we start reusing more, which is unfortunate. but this is something that should be taken into account. Yeah.
Okay, thank you. Now the second question is, if we add module D to another module, for example, module A, would this constitute double counting, or how should the module D be interpreted if it cannot be compared with the others?
Yeah, first of all, it is double counting, but also it is telling completely different story. Module A, B, and C is just LCA within its own boundaries. So this is everything that happens actually in one life. Module D is kind of system expansion. But if you add module A to module D, you will lose the information about module A completely, because module D is the difference between module A of new building and the old building. So basically your results will look like the recycling impacts exactly. So if you want, for example, one indicator to tell how sustainable or how low carbon footprint is of your product, and one indicator saying how much circular you are, you cannot have one number. You must look at them separately. Yeah.
Okay, thank you very much. I hope that answers all of your doubts. Now let's go to the final presentation, which is going to be done by Angela Daniela de la Rosa. Okay, so she is going to be speaking about environmental impacts of different energy sources in the production of steel components, which is a Norwegian case study. So Angela, the floor is all yours. Please go ahead.
Thank you for the presentation. Thank you for inviting me to do this talk. Do you see my slide?
Yes, we can see it.
Moment. Okay, I'll put it in a presentation mode. Okay, so my name is Angela Daniela La Rosa, and I'm professor at Norwegian University of Science and Technology. And today I'm going to describe a case study on LCA application for production and manufacturing of steel component. And this study actually was done together with one of my students who was at that time working at Stamas Solutions, that is a Norwegian company that is specialized in production of steel components. So the question came to the company actually. The company want to understand how much was the impact of the product of a specific product, and they wanted to understand if they could do or take any action to try to reduce the impact of the manufacturing process. So as you know, for sure, the steel production manufacturing process is mainly done by two routes. The most known, known route is the primary route based on the use of iron in ores and use of furnace, blast furnace, oxygen furnace, while the other route that is based on recycling scrap and is the electric arc furnace. It's an alternative route that is becoming more popular, but because it is more environmentally friendly. And as you can see in this slide, in 2023, 30% of the steel that was produced using the electric arc route. So in my case study, the methodology used was the electric arc furnace. And the benefit of this method is that, of course, using a scrap means that there is a reduction in the unavoided, there are avoided impact due to the fact that you are not using virgin materials, but still the process to make the component requires electricity, so there is still a certain amount of impact. So the case study is based on the analysis in deep analysis on how the energy or the source of energy can contribute to the final impact, and not only the final impact. I will explain briefly here what is the component. First of all, the component is this that is called pap joint, and is produced by Samas solution. It is made of low steel alloy, the IEC 4145H. And as I said, it is produced from recycled scrap. The thing is about this product is it's not produced entirely by Stamas solution, but this component, if you see here at the system boundary, has in the system boundary there are different processes to obtain the final product, and all these processes are done by different companies in different countries. So actually what Stamas Solutions does is the final step, this CNC turning, but all the other steps like the electric arch steel production, hot rolling, quenching, these are done by other companies in different European countries. I cannot mention the countries because the Samas doesn't want to disclose this information, but they are based in Europe. So the material actually has to travel quite a lot before moving to Norway, and before the Norwegian company produces the final step. This study was also published, and if you are curious, you can read it. It was published in this CHIRP Journal of Manufacturing Science and Technology recently. And so I'm going to present actually the result of this study. And two words about Stama Solution is a very well active company in Norway, specialized in CNC machining, especially for drilling and well equipment like pop joints and others. And I'm very glad that the company actually had this question and allowed me to do this study, because we got some primary data for the analysis, and me and the student could make interesting modeling for all the steps that are involved in the manufacturing process. As you can see here, we have used data from the EcoInvent dataset, and but we collected primary data about energy consumption, emissions, and so on. And I guess that you all are familiar with this DLCA tool. So I've used also the Sima Pro software. One result of the simulation, this one that I'm showing. This is a network on the production of pulp joints across Europe, let's say. And so you can see here the contribution of the different steps. That is the electric arch production, hot rolling, quenching, CNC drilling, and turning. All this data involve transport. The transport was also added, as you can see here. Transporting this material actually has a contribution, and but of course the biggest contribution here is the electricity for the electric arch production. So the final the total amount for the production of this pap joint is 466 kilogram of CO2 equivalent, which seems to be quite huge, considering that we are already starting when the process is already using scrap materials. So the question of the company is how can we reduce this impact. Actually, the company was want to know if doing all this manufacturing step in Norway could be beneficial, because in this case the transport could be removed. And of course, the answer is yes in this case. If all the process is done in Norway, the transport will be removed. And in this result, you can see the impact, the results of other impact categories other than the global warming potential, and these are defined for each process step. I move forward because I don't want to spend much time on these results, but I want to mention how the energy sources can modify the impact on the production, and this also to answer the company, because the company asked me, what is it beneficial if we done all the manufacturing step in Norway rather than across Europe? One reason is yes, because of the transport will be of course removed, but another reason is the energy country grid that is used. As you know, I don't know if you know, but in Norway has the country grid, electricity country grid, that is based on hydro, on water. So this is very ideal situation, but in the average country mix of European countries is based on fossil. So I have taken this Italy as an example. Sorry, I've taken Italy as an example to show how in Italy the majority of the source to produce electricity is fossil, and there is few amount of renewable, and the impact of producing electricity in Italy this is the table of the impact to produce the energy electricity in Italy. I was comparing these results with the other type of sources, like I compared the country mix of Italy with the hydro. Of course, these tables are referring to the production of 1 kilowatt hour of electricity, and you can see here that the production of 1 kilowatt hour using the country mix of Italy has 0.4 kilogram of CO2 equivalent. It's almost the same as using natural gas through cogeneration process, while using the photovoltaic as 0.06 kilowatt hour at 6.6 kilogram of CO2 equivalent, while using hydro is very negligible, as well as nuclear. But when we go, we look at other impact categories, we have to, we see that, for example, if you look at land occupation, photovoltaic has quite high impact compared to other sources. And when we look at the becquerel equivalent, this is basically the radiation, the nuclear source has quite relevant impact compared to the others. And also when we look at the water toxicity, aquatic toxicity, all the other all the energy source used have impact. The lowest impact is always hydro. So the ideal source for producing electricity seems to be hydropower. And here I have put together in this diagram, the most used sources to produce electricity without fossil. And here you can see that for all the impact categories calculated by the CML method, but the hydropower seems to be the best. So in this sense, I did a simulation of producing the pump joint entirely in Norway, using the country grid of Norway in all the steps. So this simulation is not like a realistic case, but is a simulation. And the results, so the CO2 equivalent for producing the pump joint is 215 kilogram of CO2 equivalent, which is much lower than the result found for the real case. The real case, as you said, is the pump joint is produced in Norway. In each country, of course, each country uses the national country mix that is mostly based on fossil or nuclear. And in Norway, uses the hydropower. So there is a big reduction. In this reduction, also transport is accounted. And also you can, in this slide, you can see also the damage, of course, is reduced for if all the entire production is done in Norway. And in this slide, I want to show, I made a comparison on the impact of three cases, three scenarios. The first one is the impact, and this one is a global warming production in the case of producing steel from virgin material, from iron in ore. And so the CO2 equivalent is quite high, it's 2,390. I have used here data just from the eco-event database. And so for using the electric arc steel, the impact is 465, and while using the all the entire process of using the or for the production of the pump joint in Norway, the impact is reduced again. So for each impact categories, you can see for also that there is a reduction of impact when all the manufacturing is done in Norway. The abiotic depletion as well. I want to show the abiotic depletion because here it's highlighted the fact that using the electric arc furnace, there is no impact on raw material consumption. There is lower impact because there is a less raw material consumption. So basically, I mean, this was the answer to the company, but also and so going to the conclusion. So the hypothetical scenario of creating an industrial park in Norway to produce for steel production is very beneficial because of the use of renewable energy, but also to remove the transport. And this solution is in line with the concept of industrial symbiosis and circular economy that is based on maximizing the exchange, the physical exchange among the value chain. And finally, I consider from the academic point of view, I consider the application of the LCA in the manufacturing processes very beneficial in order to increase the knowledge and also to develop the next generation green skills, as you can see here, which is the new society with a better knowledge on how to go towards sustainable development. Being an academic, for me, this is actually the main goal, to introduce this concept on LCA to students of engineering, and which is quite difficult because they are two different topics. Talking about sustainable development goals or sustainability, Norway is very much committed in this. In fact, I'm showing here the results of sustainable development report from a few years ago, and among the EFTA company, among the European country, Norway that belongs to the EFTA countries, Norway scored 5 as a sustainability index. Was number 5. And you can see here that most of the Sustainable Development Goals are reached. And also from the result from last year, the Sustainable Development Goals were scored better. And if you consider all the OECD countries, Norway is in 7th position. The first position is in Finland. Anyway, Scandinavian and European countries are scoring very well. And I hope that this trend will be promoted, will still continue. And yes, I finished my presentation. Thank you for your attention.
Okay, well, thank you very much, Angela, for your presentation. That was very complete. Let me see if you have any questions here. Yeah, we have one here. It says, well, first of all, thank you for your presentation, Angela. It says, did you consider using residual mixes for the electricity modeling to prevent the same MWH from being claimed twice?
Let me read. Is the question written here?
Yes,
using residual mixes for the. No, actually, I just used. This was a simple exercise, and I used the data from the EcoInvent. Okay. Yes, of course. I didn't. I was very careful in the simulation to prevent double counting. Yes, the simulations were done very accurately. I manipulated a little bit the EcoInvent to remove the data that were like double counted.
Okay. Thank you very much. I hope that answered your question. As we are about to finish, I would just ask for a little favor from all of you. If you wouldn't mind opening your cameras and showing yourselves so we can take a picture of the workshop attendees and post it up in our social media platforms later on. Angela, you can now stop sharing your screen, please. Yeah, thank you. Okay, so, well, let's take the picture. Okay, let's go one more. Yes, thank you, that's it. Okay, I think this will just wrap it up right here. I don't know if Nethmi, you want to say something else, or
Yes.
we can just finish it out. Okay, yes,
I
we
would
hear
like to say thank you to all the speakers. They were amazing presentations, and I guess we all learned a lot today. And I also want to say thank you to the people who attended today. I hope this helped, and I'm glad now that I've connected lots of people together from different countries to talk about steel. And hopefully we will meet again to do more webinars like this. But thank you very much again for being here and for your valuable input. Thank you.
Okay, so if there's nothing else, we will be sharing this webinar on our YouTube channel, hopefully by the end of the day. So those who couldn't be here today will be able to watch it and share it and make questions, and hopefully we'll get back in touch with all of them. Okay, so thank you very much for being here, and I hope to see you again in another workshop. Thank you.
Thank you. Bye-bye.
Yeah, bye-bye.
you.
Thank
Bye.
you.
Bye-bye.